everyone. Let's fire off our slides for today. Welcome back. Got a bunch of stuff going on. And okay. Looks like everything's fired up and looks like we're broadcasting okay. So welcome to Westmont College Mayterm. We are live from Santa Barbara. We are coming back from Memorial Day, and we're not, I don't think, 100% here this morning yet. Still waking up, still getting back into the groove of things, still trying to find parking in some cases. This is broadcast live from Winter Hall. This seminar is part of a 5-week class teaching Java. This is our CS-030 class taught over Mayterm. Today we're going to have a lecture that's scheduled for 2 hours, and we're communicating in real time if you are on our Slack channel on #broadcastquestions. And otherwise, we can give a shout out to the folks who are joining us in Southern California and around the world, including, I think, Flo's still in Santa Barbara. So, yo, hello out there. We need to arrive, so let's just take a second and make sure that we are here and present and our notifications are set as we want them to be. Mine are off, and I think they're off. There we go. And we've been talking about regulations, but since we're coming back from break, I just want to take a second and open our week and kind of the final 2 weeks of class with the prayer that we've been saying before, said at the beginning of class. And we'll just start with this again today. So, we're just about to, welcome Tim, we're just about to arrive. Turn off your notifications. All right. O Lord, grant us to greet the coming week in peace. Help us in all things to rely upon your holy will. In every hour of the day, reveal your will to us. Bless our dealings with all those who surround us. Treat us to treat all that comes to us throughout the day with peace of soul and with firm conviction that your will governs all. And all our deeds and words guide our thoughts and feelings. In unforeseen events, traffic, parking, whatever it may be, let us not forget that all are redeemed by you. Teach us to ask firmly and wisely, act firmly and wisely, without embittering and embarrassing others. Give us strength to bear the fatigue of the coming week, 2 weeks, with all that it shall bring. Direct our will, teach us to pray, and you yourself pray in us, to the glory of the Father, and of the Son, and of the Holy Spirit, now and ever, unto ages of ages. Amen. Okay, so administratively, we had our exam last Friday. It was actually kind of pretty consistent. Everyone scored more or less the same. There's a little bit of variation, of course, but it was in the ballpark. We did a proctor-free trial, and the proctor-free for the folks that were remote seemed to go okay. We have one person who had a glitch and is still out there taking it. So the grades are on Canvas, but I won't give you back your paper exam probably until next class, just because we have one more student taking it. We're going to do the same process for the final exam. So you guys will take it in class. The final exam is on June 8th, which is the last Friday of Mayterm, like a week and 4 days from today. Remote people, you know who you are. You'll be doing it from Proctor Free again. That process seemed to be okay. Between now and then, we've got a lot of work to do, though. We have a programming assignment on Chapter 18, which is about generics, which we're going to start talking about today, due on Friday, and a quiz also on Friday. Same two things. You know what we need? We need some cheering. Great. And we, this week, are covering 2 lectures on Chapter 18. We're going to do 2 lectures on Chapter 13, which is recursion. We're going to talk about the drone programming assignment next Monday, and then we're going to spend 3 days on tree structures, Chapter 17, next week. The drone programming assignment is going to be, usually if we do this in a longer form course, we do 3 different assignments for that. We're just going to do 1 for our Mayterm because there's enough, it takes a little bit of time to get your head around how to program it. So we'll talk about that next Monday. Anything else about administration or how the exam went? Seemed like everyone had enough time, so that's a good start. Okay, great. All right, so last time, remember, if you can recall, way back in the day, we were talking about, we implemented linked lists and we implemented array lists, and we did that to help us understand the efficiency trade-offs of how and why you might implement them in different ways. We saw that linked lists were built out of this thing that's down here at the bottom, a master header node, that linked list node there. And then we also had these individual nodes, that's our master node there. And then we had these individual nodes here, which actually held our data. And they were linked together by this next link, so that whenever you wanted to add a new node, you didn't have to deal with the entire list. You just had to find the place where you wanted to insert it, create a new node, and then drop it in there by adjusting the next and the next links like that. So that was a particular one feature of that made it efficient. We also implemented stacks and queues with our lists. So we used this list idea, which is the list is an interface. It just describes a behavior. The implementation was done with a linked list or an array list. And then we implemented stacks and queues with this abstract idea of a list. And we saw that as long as you have that behavior of a list, you can build the stack or the queue behavior on top of that without having, it was like 2 methods. It was pretty easy. I thought it was pretty easy. Your mileage may vary. And so that was our singly linked list, but we also talked about what a doubly linked list might look like, and that's here at the bottom. And the difference between the singly linked list and the doubly linked list was those next and previous links that were in each of the nodes. So they linked forward and they linked backwards. You may notice up here that there's a last and a first link on that header node. Whether or not you have a last and a first doesn't distinguish a doubly linked list. So you can have a last and a first node in a singly linked or a doubly linked list, but typically you have them both in a doubly linked list, and you have last optionally in a singly linked list. Having a doubly linked list doesn't provide you any additional efficiency except for some very specific kinds. It provides additional functionality, enables an iterator to go backwards as well as forward, but it doesn't really drastically improve your efficiency in any fundamental way. We also implemented array lists. Array lists had a different underlying technology. They were built out of a primitive array, and so we allocated that memory beforehand, and we had to differentiate between how much memory we had allocated. So in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8 spaces allocated, but we actually are only storing 7 items. And so we had to keep track of this size variable to indicate how much of the array that we have allocated is actually being used. And when we ran out of that space, we had to double the size, or we chose to double the size of our array and copy the elements over so that we could continue to grow our list if we needed to. We also took those and then we implemented a stack. And so you'll recall a stack can be thought of as just a list where you only put things in on one side and take things off on the same side with the push and pop commands. And based on the properties of the underlying implementation, you might choose one or the other, or you might choose whether to implement push or pop by adding things to the beginning or to the end of the underlying list, depending on the implementation you chose. And then we also implemented queues, and if you recall, queues put things in on one side and took things off on the other side, but the queue abstraction doesn't necessarily dictate the order in which things come out. You add things to one side and you take them off the other side, but the way in which they travel through that isn't necessarily like a line like you would expect at a bank teller or at a car wash or something. They can come off in priority queue order, which is more like what you would experience at maybe if you were boarding an airplane with some airplane that had a whole bunch of different tiers of priority status. Everyone gets in line. Who gets to board first? Platinum, Premier, Diamond, Plum card holders, and then who gets to go next? Premier, Sapphire, Advanced Club members, and then veterans, and then families traveling with infants, and then business class, and then the cattle. So cattle goes last, but that's sort of a priority queue. It doesn't really matter when you show up in the line. The people that go first have higher priority. You can implement that with a queue because all a queue says is you put things in one side and you take them out the other. Thoughts, clarifications about that from last time? Okay, as I was going through the exam, mostly there wasn't a particular trend, I didn't think, in who was getting what right and who was getting what wrong. I actually kind of thought that this class in particular was pretty good at hand tracing, which is the process of going through code and trying to evaluate what a variable is going to end up being or what it's going to print out. Across the board, I think the class did pretty well in that, a little better than maybe an average class. But there was one thing that was pretty widely missed, and that was an issue about references and copying. And maybe we didn't talk about deep copying, but I want to talk about it today. I just want to clarify exactly what's happening when we do reference assignment and copying, because we need to make sure that's clear. So what I'm going to do is kick to an example in Eclipse and just have you follow along on the screen to sort of show what's happening. All right, so let me show you the code, and let me first orient you to what we're looking at here in the code before we discuss what the issue was. Organize our imports. All right, so we've got a main function, and we've got this outer class example, which is what we're using to run our example. Inside example, we have a helper class called geography, which can be used within the context of the class example. It can be actually used outside because it's public. But then in the main, what we're doing is we're creating a linked list, which is designed to hold these geography objects. The geography objects are up here. So what is the idea of a geography object? A geography object is something that holds a name and a type of a place. So you can see on line 22 here, what we're doing is we're creating a new geography object which maps Santa Ynez and mountain. Those two strings are getting stored together in one geography object. And then we're adding that object that we just created to our linked list. So is the setup clear? Rather than having our linked list hold strings, we're having our linked list hold objects that we've defined. All right, so in line 23, we add another one to the end. So we're using the Java version of linked list. And so if we hover over here, we can see that what add does is that it appends an element to the end of the list. And so when we add Pacific Ocean to the end of our list, we're going to have first the mountain and then the ocean. And then in line 24, when we add Los Angeles, which is a city, to the end, we're going to have city at the end. And so the order should be mountain, ocean, and city. But those are embedded within our geography objects. Now I create a new list called B, which is also the same type. It is a linked list of geography objects. And I initialize it on line 27. So on line 27, first of all, I declare the variable B, and then I create some memory that's going to hold a new, different linked list, also in 27. And then 28, I do this confusing little bit of work. I say B equals A. Hold that thought for a second. And then in line 29, I say B, set the first element in my array list, index 0, to a new geography element, the Mojave Desert. So the question is, what is the structure? If we know this was A before, what's the structure of B? Tim.
So B is going to be the same thing as A, Santa Ynez, Pacific, Los Angeles, except for instead of having Santa Ynez, it's going to have Mojave Desert.
So, okay, so like that. Mojave Desert, Pacific Ocean, LA City. All right, that's right. The confusing question is, what happens in line 32 now? What is line 32 going to print out? Because we are asking about list A, we're asking to retrieve the first element, index 0, and asking to print out the name of that first element. Okay, what happened?
Is it? I mean, it obviously used Mojave Desert instead. Is it because when you set B equal to A, they start like containing the same space or something?
Yeah, that's right. On line 28, when we set B equal to A, we didn't make a copy. We have two references that are pointing to the same spot of memory. Let me see if I can try and draw that out. I'm not my second grade drawing here. So we started with A was pretty clearly 3 elements. And then when we created B, let's see if I can show that real quick. On line 27, when we created B, here, let me, in the background, I'm just going to update with the type. So we had mountain, ocean, city. Okay, and when we created line B, we actually created a linked list, but there's no elements in it. So I'm going to just sort of make a box there because that's like that's the linked list, but it has no elements in it. But then when we said that B equals A, we changed this reference from pointing to the linked list that we made, and now we pointed it to here. So this now gets cleaned up by the garbage collector, and B and A now point to the same linked list. So in line 29, when we set B, we said B.set 0 to Mojave Desert, we ended up changing this element here to be a desert instead of a mountain. But now B and A are both referencing the same memory. So when we ask for what the 0th element of A is, the 0th element of A and B are exactly the same now. And so we end up having 2 references to the exact same data. That can end up being a real confusing point if you can't get your head around it. Now, maybe that wasn't what you wanted to do. Maybe what you actually wanted to do was you wanted to create a copy of that list instead. That's sort of reasonable, but you wanted to create something that's the same, has the same data, but you can manipulate independently so they don't mess up. Well, there's a couple things that you could do. You could do something when you created it, you could say, pass it A, and then that's going to create a copy of your data. So now we get what we expected to get, which is the Santa Ynez Mountain remained the same, so A didn't get modified. The other thing that you could do is you could do collections.copy A, copy A to B. So that's sort of explicitly doing the same thing, unless I did something wrong. Source does not fit in destination. Okay, take it back. We have to make enough space in B in order to hold A before we can do that. So let's just stick with this example. So that's actually going to make a copy of A. And so in that case, what we're going to end up with something different. We're going to get that B now has 3 separate items that contain the same data. Okay. And those, you can swap those back and forth. I mean, you could do something sort of nutty and just, let me go back to the code, go back to the code. You could do something sort of crazy and do this. Let's create C. We're not even going to allocate any memory for C. We're just going to say that C is a reference. Now we'll say C equals B, B equals A, and A equals C. And we just ended up swapping the 3 different references. Why isn't that compiled? Oh, sorry, let me make this less. There we go. So that ended up just swapping the references. I mean, there's not going to be a huge effect of that, but what we did is we took A and B, we created this new variable C, and we said that C is going to equal A is going to equal B is going to equal C, and we just swapped all the arrows around. So the memory is all staying in the same place, but we ended up having all our references pointing to different items. And that is possibly helpful in some cases if you want to do various kinds of manipulation of your list. There's also an issue of the fact that we're not doing a deep copy in this as well. Let me see, kind of not totally prepared to communicate this, but let's see if I can try and explain what a deep copy is.
Before you do, why would
Yep.
you want to have 2 lists that are both empty point to the same reference, the same space?
Well, it might not be necessarily that that's something that you want, but it might be something that ends up happening. So for example, if I end up creating a method here, and let's say it's a private, returns nothing, mm, oh, for clarity, let's see. Okay, so what I've done here is I've made a method called helper. And helper takes as a parameter this list C. And so if you look at line 33, A is a reference to a particular list. And then when I call line 19, C and A are now references to the same bit of memory. So it's not that I wanted to create another reference. It's that in the process of calling this method, I created another reference. So then on line 20, when I set the 0th element of C equal to Mojave Desert, I'm simultaneously modifying what A points to along the way. So do you see line 33 where I call helper? So when I'm in the body in line 20, A and C are pointing to the same bit of memory.
Yeah. Why would you want to do that, though?
Oh, well, any kind of method that needs to manipulate your list. Like if you want to make some sort of method, what if you want to make a method that sorted your list, for example? We actually have that, right? We could do collections.sort A. And that will sort the list A, notwithstanding the fact that it's not comparable. But in principle, that will sort the list A. But in order to do that, it's going to have something like line 19 where it has a parameter that it's receiving. And so internally, it's going to have a reference to the same thing that A is referencing.
Right, why would you want to change to list one empty list to another list? Because isn't that redundant?
Well, so let's see. In this example here, I could do this. Is this what you're asking? So in this case, now I have two references to the same list. B and A are pointing to the same thing. And why would I want to do that? Is that your question? I'm not arguing that you do want to do this. I'm arguing that you can do this and that this ability to do this is used when you pass a list to a method. So in line 33, when we call helper A remains a reference to the list, and then in the body of the method in 19, C is now a reference to the same thing, but you're now manipulating A with a different name, C. So it's more like just an effect of something that can happen rather than why would you just want two variables that do the same thing in one method. You don't really want two variables that do the same thing in one method. You would maybe want to make a copy of it so you can manipulate it separately. But this is a feature of the language that you have to make sure you have the right mental model for, so that when you call a function like line 19, you know that that method, that helper method, can change the thing that you passed in. Like the thing that you passed in isn't protected. It can be modified. Okay. So let me see if I can describe in a nutshell what the deep copy issue is. So if I complicate this a little bit, and I say that our linked list was a node like this, remember? And that had this first element, and that pointed to a node. And the node had an element that pointed to our geography object, which had something like mountain and a name. And then it had a next element that pointed like this. And that had an element that pointed to the ocean. And the linked list had another element that pointed to its final element in its linked list, and that pointed to the city element. We said A is going to point to this linked list element here. When we make a copy of B, when we make a copy of linked list A, we get what's called a shallow copy, which is that B is going to get its own header called first, and it's going to get its own 3 nodes. And that's as far as the copy goes, but it's going to continue to point to the same geography elements underneath, but it will keep them in their own order. So that means that it's possible that even though you've made a copy of B, you can go through this element and change an element of A nonetheless, because we did what was called a shallow copy. Shallow copy is just copying these elements here. So let me see if I can demonstrate what the shallow copy is not doing for us. All right, so we have A. We've added 3 elements to A. And now let's create B. And B is a shallow copy of A. So B and A each have their own ordering, but the things that they're storing are the same 3 elements because we've only created 3 objects here. We haven't created anything new. They're just 3 objects. And so we can do things like say, let's say b.remove position 0, and let's store the element that we removed. And what should that be? That should be the Santa Ynez Mountains. And it is. And then what we're going to do is we're going to say b.add that Santa Ynez Mountains that we just took off. So whereas A is MOC, B is now going to be OCM. Buy that so far? So far, so good? Okay, now what we're going to do is we're going to say b.get the last element, so that's the element we just added, and we're going to set its name equal to Tim. And we're going to set its type equal to student. Hardly a geography, but it's okay. Now what's going to happen when we try and do system.out.println A get 0 name and A get 0 type?
It's going to do it for the first one. No?
Yes.
Maybe? Wow.
We remove 0, so it's going to give us the specific ocean.
Tim student. Yeah. I'll wait for.
So A and B each have their own ordering, but the objects that they're storing are the same objects. They're just in different orders. And so what we did is we went into B and we went to the 3rd element, index 2, and we changed the name and the type of it. And although it's in a different position, it's still pointing to the same object that was created in line 27. So if we wanted to have a completely separate list that had no references to any of the other objects, we'd have to do something called a deep copy. And a deep copy is something that's typically not implemented for you because of the complexity of actually copying your own objects entirely. But we could write something that would do a complete deep copy if we wanted to. And in fact, in the drone code, I actually implement my own deep copy so that when I allow you as a programmer to control the drones, I don't want you messing with my data structure. So I give you a complete deep copy of it so that you can make your decisions and do whatever you want, but it doesn't mess up my references. Okay, so that's, I guess, an introduction to the difference. Whoa, that's a little fast. We're not quite done yet. So that's the difference between the reference. The important thing to understand is when you set A equal to B, you're referring to the same memory. You can copy things, And you need to know that there's a difference between a shallow copy and a deep copy, even if you don't totally have your head around what that means at this point. Okay, so great. That is bringing us where we were. Now what I want to do is I want to pick up on material for today, which is on generics. I think generics are pretty neat. I think they're a pretty powerful abstraction that you get to use in Java. They're not unique to Java, of course, but they're certainly used a lot. And let me see if I can start by motivating what the rationale is for generics in general. So at the highest level, we've already used them. We've seen them. We've seen them when we did things like said array list and put in angle bracket strings. That thing that we're putting in angle brackets was the generic. So what generics do is they enable types, classes and interfaces in particular, to be parameterized, meaning we can take the type and we can parameterize it by string or some other kind of type. And so the input to a generic is a type, and the output of a generic is a new composed type, a type that is your base type, like linked list, and the parameterized type, like string. They're a lot like parameters and methods in that you sort of pass this element to another entity, but they're not about data. They're just about type checking, and they're not values. What they are is they're metadata about the object that you're working with. And they let you write the code one time with different type inputs so that you don't have to have a whole bunch of different kinds of classes around for every different kind of type you want. So the benefits of generics is that you end up writing less code. You do a lot of code reuse because you can create lists and array lists and stacks and queues of all different kinds, but you only have to write the code for stacks and linked lists once. And they enable programmers to implement these generic algorithms one time. And so if you have bugs, you can fix them in one place, and you don't have to worry about bugs proliferating over all these different copies of your code that are being used to create types with different underlying parameterized types, I suppose. They enable us to do stronger type checks at compile time, and that enables more errors to be found at compile time through static checking. So remember, compile time is when you're programming. The worst thing to do is to have some kind of a product that you're making and to deliver it to a customer and have that product crash on the customer, whether it's a paying customer, whether it's a nonprofit, whether it's just people that you volunteered to make. Because there's enormous amount of overhead and cost one way or another, time or money or just the messed up world that you just contributed to, if you don't fix your bugs before you ship. And so a great thing that generics enable you to do is to identify more bugs before you ship things out. So let me see if I can demonstrate this with a little diagram here. This is an example of what happens when you've got code being written and then sent out to the world. So on the left there, you've got your developer, and your developer is working on a computer through an IDE like Eclipse. And the developer is creating code like the code in the upper left, where the class foo in this particular case. And as the developer is typing, Eclipse with Java is compiling that in the background and trying to find syntax errors and bugs and other things that the programmer might be doing wrong. And if the programmer has written it okay, the compiler is going to allow that code to go through, and it's going to create bytecode. This is either a .class. It's typically the .class version of your .java file, but when you put several classes together and distribute it, you put it together in a jar file. Jar stands for Java Archive. You put that together and then you distribute it. How do you distribute it? Well, different ways. You might put it on your website. If it's an Android program written in Java, you'll put it up on the Google Play Store or some other mechanism. However, it ends up getting in the hands of the guy with the scarf over there, Santa off duty. That person is going to receive the Java code on their computer where they have a Java virtual machine running, whatever their operating system is. They're going to take that bytecode and they're going to run it. And if all goes well, terrific things are going to happen as a result of what that programmer did. This is a bug-free world. But let's take a look at something that can go wrong. So in the top example, we have an example of a list in which we're not using generics, in which we have to do an explicit typecasting of the contents of our list. So let's take a look at what's happening there. We have a list being defined here. It is of type list with no generics. And And we're saying that reference list is going to be given a new array list object that we're creating here and calling the constructor. So this gives us some something to work with, but there's no elements in it. It's length 1. Then this next line here, what we do is we add an element to our list. We add the string hello. We're not using generic, so we don't know much about the contents of our list, but we know that we just added hello. So down here, when we ask to get the 0th element, the first element, index 0, what we get back is an unknown type because we have no types defined in our array list. And in order to use it as if it was a string, we have to do this bit of typecasting here. And what this does is it says, hey, compiler, when you give me back the element at index 0, I want you to treat it like a string. And so even if it's not a string, we don't know if it's a string or not because we don't have any guarantees about what types are being stored in our list. I want you to treat it like a string and give me a reference S that's going to point to it, and that's going to have methods that I'm going to assume that I can call. Now the problem is, if that's not a string, then I have this reference S pointing to something that isn't a string at all. And if I try and call a string method on it, it's going to crash because it's not a string object. But when we rewrite this with generics, we get much stronger code because we say that the list is going to contain strings. And when we construct it, we're going to construct it with an implementation that explicitly contains strings. And so here, when we try and add something to our list, the compiler can verify and say, hey, you're not allowed to add anything except the things that you said you were going to add here. You said you were going to add strings, so I'm going to check to make sure when you add something that it is a string. And furthermore, when I give you something back, because you committed to adding strings here, when you get something back, it's going to be a string for sure. And so you're not going to you don't need to cast it because you know what list contains its strings, and you also know that when you call methods on it, that they're going to work because it's actually a string type. So let's take a look at the code on the top. And what I would like you to do is I'd like you to just maybe pair up, or we've got a relatively small group here so you can work through it on your own. I want you to look at the code on the left and the code on the right. And I want you to do a think, pair, share exercise, which is where you look at it by yourself for a minute and then pair up and talk about what it is that you see, and then I'll ask you to share what you guys found. All right, we'll go offline here in a second, but let me just walk through it. I want you to look at the code on the left and identify what it does, and then identify what's different about the code on the right, and answer if the code is syntactically correct, meaning is it going to compile okay? And then we'll then after we take a second to do that, we will move on. So what I'm going to do is we'll just take 2 minutes. We'll take 3 minutes actually, and we'll take 1 minute for everyone to look at themselves. We'll go offline. We'll take 2 minutes to share, and then we'll come back online and have a discussion about what's different. Okay. So let's see. We're going to go offline for a sec. Be back in 3 minutes. we're on. All right. So we had a little bit of a discussion here. Maybe I'll call on someone randomly here. Hey Siri, pick a random number between 1 and 4.
That would be 4.
All right. Boaz.
Uh,
Okay, so let's start by just trying to, and you can call a friend or a lifeline or 50-50 or whatever game we're playing. What is the code on the left trying to do, regardless of whether it's accomplishing it well or not?
So, it's checking to see if the length of a word is less than 4.
Greater than 4.
Or
it's adding, or it's finding out how many words are longer than 4.
Great. And if it finds a word that is longer than 4 characters, what does it do to it?
Then it makes it the longest, or it prints it, and
Well, first, it does something to it here. Here. What's happening there?
no, it adds it to a list.
It adds it to a vector, which is very similar to a list, but yes.
Okay, yeah.
All right. Okay. So this thing is going through. It's looking at all of the incoming args that are an array of strings. It finds if any are greater than 4. It adds it to this data structure long words, and then what's happening down here?
Then first string is 0. It's a for loop, making it so that is string word. So it's making the long words into a string, right?
It is. Yep. So it's doing a typecast because there's no generics here. We don't know what it's being stored. So it's casting it to a string.
And then it prints out that string plus length and then how long the word is.
Okay. So in principle, this code is collecting all of the words that are greater than 4 characters and then printing them out. Now, in this line here, is long words ever going to have something in it that's not a string? No, that's tentatively said, but accurate, yes. So here we create the data structure. Here's the only place where we add it. The things that we're adding are only strings, and so longwords is only going to contain strings. And so down here, when we cast it to a string, we're never going to run into any trouble. Now that's not being supported at all by the compiler because we're keeping track of what's being stored in long words. The compiler has no idea because we didn't say as much. All right, so let's go to our neighbor here. Hey Siri, pick a random number between 1 and 4. I slurred. Hey Siri, pick a random number between 1 and 4.
It's 3.
Okay, Tim.
So if it picks 4 again.
It could have. What's the difference between the code on the left and the code on the right, except for beside the method name?
Sorry, the method name. So in the code on the left, they add they add every element inside of the argument that's passed to it.
So here.
Yeah.
Okay, not every one, but those where the length is greater than 4.
Yes.
Okay.
Yes. And on the left, they do the same thing for every.
On the right?
For every time there is a word with the length that is greater than 4, they just take every argument that's passed, and then so every word that they'll just put in the list multiple times, every single time for the.
Great. So every time it encounters a word that's greater than 4, it's going to put a reference to the entire array of all the words into long words. So if there are 10 words that are longer of length 4, long words will contain 10 references to all of the data that's been passed in. So this is pretty clearly a bug in as much as what this is trying to do is keep track of the long words. So Is this code syntactically correct? Is it going to compile okay?
Yes.
That's correct. It will. Because down here, when we get an element from I and we cast it to a string, the compiler has no information about what long words is going to contain. We know it's a vector, but we don't know anything about what's in it. So when we cast it to a string, it's on us to make sure that it's going to be a string. The problem is when we run it and we ask what word.length is, or we try and print word, we're not going to get anything that looks like the methods that you would call on a string. We're going to get the behavior as if we just called word.length on an array. And because this isn't a method that you can call on an array, this is going to crash. So let me just reiterate that. This code over on the right is going to compile fine. But when you actually go to run it, it's going to crash. Okay? Compile fine, but when you run it, it's going to crash. So actually, I'm not going to try it. So what that means is we've gone through this process here with the green check marks. We've had our developer create the code. We've had the compiler check off on it. Maybe we didn't recognize that when we ran it, that was going to cause it to crash because maybe that was an unusual piece of code that didn't get run in our testing. We distribute it, and then our off-duty Santa runs the code and it crashes. And now off-duty Santa's got this bit of code that you created, and it's kind of worthless. First of all, the code looks like it's unprofessional. It's not doing what they wanted to do. And if you needed that off-duty Santa to be a customer for you, you've just lost your customer for whatever kinds of enterprise you're engaged in. So that's a real problem. So let's take a look at this code then. What's different about the code with generics now? So the left side is the same good code we saw before, and the right side is the good code with generics. So let's just take a minute to look at what's happening there and to recognize what's different. Okay, Lisa, could you tell me what's different about the code on the right? Right, so you're looking right there and right there. That's the bit that's the generic. So when you put things in angle brackets, that's the generic type parameter. And so what that's doing is it's saying that, okay, you're going to have a vector, but you're committing to it containing only strings. And so by declaring that, the compiler is now able to enforce that. It's able to enforce that right here when you try and add args I, it's got to be a string. And if you tried to add args without the substrings, the compiler would check that and would know it because you had declared that this is only going to contain strings, not arrays of strings. And so down here, when you end up getting your ith element, you don't need to cast it because the compiler already knows that what it contains is strings, and it can enforce that right there. All right. So now, if we take that good code with generics on the left, I moved it from the right to the left. We have the generic code on the left. And now we introduce the same bug that we had before in the bad code, but now we've declared it with these generics. you can see that the compiler does the catching for us by underlining the bad code in red. So we declared that we were going to hold strings in our vector. And when we went down here to add something to our array, we forgot the subscript. And so we get this little error here. And what Eclipse would tell us if we expanded that bug there is it would say, hey, you're trying to add something to the wrong type. Args is not of type string. There's a problem here. And so you've stopped a bug from getting out into the wild. Right? The compiler has helped you because you've done the work of declaring what it is you intend to store in this code along the way. So what that means is in this tool chain, in this distribution plan, the error has been stopped long before it's been distributed. You've been able to keep the code from going into the wild. You don't have a bug that you might otherwise have had. You've saved a lot of time and possibly money by not having code going out there and not having to do a big public relations campaign for why your code is still professional even though it crashes on everyone's machine, et cetera, et cetera. Okay, so what I think is super cool about the code on the left is that when the developer made that vector class, the developer had no idea that what I was going to be storing in it was strings. They developed it generically, as if I could store anything in it. And inasmuch, I could have done what I did on the right. This is code with generics as well, and you can see that I've created my own class called identity, not shown in the code, but referenced. And now I've got this vector that's full of identity classes in which I'm keeping tall people. And instead of going through a bunch of arguments that are strings, I'm going through a bunch of arguments that are identities. So you can see that's getting passed in up here. And instead of checking the length of my words, I'm checking the height of my people. And assuming that an identity class has something called getHeight, and it's stored in feet, I suppose, I'm keeping track of anyone who's over 6 feet and adding them to my tall people vector. The vector developer didn't know that. They had no idea. But because they implement it with generics, I could keep anything I want in it. And I could keep anything I want in it, and the compiler can make sure that I'm doing the right thing when I put things in and when I get things back, but the developer doesn't know anything about identity, doesn't know anything about what that means. A vector is an array list that grows and shrinks. So in our example of array list, we saw how when it got bigger, it would double in size and we'd fill it up. A vector, if you remove things, it'll shrink as well.
Oh, okay, cool.
It's part of the Java collections framework. Okay, so here's an example of what the identity class might look like. This is just my implementation of the identity class. And you can see that it's got 3 instance variables, a stored name, a stored password, and a stored height. I note that you never actually want to store a password anything like this in real code. This is just for an example. Storing passwords in your code is a really bad, storing them in clear text is a really bad thing to do. Nonetheless, this is an example in which I do it. So we've got a constructor that takes in a name and a password, and we're going to keep track of them and the instance variables. That's in our constructor there. This is what I'm looking at. And then we've got some accessors where we can get the name and we can get the password out of our object. And then we've got setters where we can set the name and set the height of our object after we've constructed it. So when we construct it, we're going to set something, but then we can change it later on with set height and set name. And then finally, down here in the set password method, we have sort of a nominal nod to security, where in order to set the password, we have to pass in the old password and we have to pass in the new password and make sure they're equal before we change the stored password. All right, so that's just an example of what we could have stored instead of a string or instead of anything else we wanted. So just to reiterate the pieces of our method signature here, our method signature has got our visibility, so public in this case, so anyone can call this method if they've created an identity class. It's returning something that's Boolean type, so true or false. The method name is set password, and the full name would include the class name. So the full name would be identity.setPassword, but within the context of identity class, set password is okay. And then our parameter list has a type for each of our parameters, and then the parameter name. So generics end up being the small language within a language, so a small language within Java for declaring types. So you can see that we've got Boolean, string, and string. Those are the types that we already have. But what we can do is anytime we have a particular type listed, we can actually replace it with a generic if we do it the right way. So let's work through that. And what we're going to do is we're going to show that people have first and last names, which are separate than their stored name that was in our identity class. All right, so we'll look at that code here in a second. But before we do that, why don't we just, we're about halfway through. Why don't we take a 5-minute break to stretch, get some water, coffee, whatever you need, and come back. So we'll be back in 5. Sound all right? Okay, we're back. And what we're doing is we're taking that idea of that vectors. We started with the vectors and we looked at how adding a specific generic type to it, like identity, was cool because it enabled us to store identity classes. And the developer who wrote the vector class didn't know that we were going to store identity classes. And what we're going to do is we're going to change our actual identity class to think about the way in which we might want to alter this. So here's our existing code. We've got a stored name, but what we want to do is we want to augment it so that that name can be a first name and a last name. So we don't keep it all as one big mash string, but we keep them separately. All right. But we know that it's not just strings or names that we want to keep as two pairs. We might also want to do other things as well. For example, keep track of height as feet and inches, in which case we have a pair of things just like we have that as well. So what we'll do is we'll create this helper class called pair. And in pair, what we'll do is we'll have two instance variables, stored first and stored last, right up there. And we have a constructor where we're going to save them. And we have a getter and a getter and a setter and a setter. This is a real basic class just to put a couple things together. Is it clear, the intention here? Okay. Real basic pair class. And so what we'll do now is we'll take that pair class on the left and we're going to use it over on the right side. So what I did is I changed the type of stored name. So that stored name up here is no longer a string type, but now it's a pair. And this pair over here is what we're going to use in order to implement the stored name. So now when we construct our name, when an application programmer uses our identity class, they're going to pass in a first name, a last name, and a password. And then our internal variables, we're going to create this new pair class where we'll pass in, we'll forward these parameters. We'll take the first name that was passed in and we'll pass it to pair, and the last name passed into a pair. And then we'll store a reference to that pair here. And so internally, we'll have this nice class that is going to keep these two things together for us. And we'll abstract that into just this idea of a name. And then password will be as is. And height will be height for later use. So pretty helpful class. Helped us to do a better job of keeping track of our data. Agree? Sure? Sure it's not a trick? Okay, it's true. This is a good idea.
Why would you want to trick a spirit professor?
Well, I'm going to have to trick you coming. I'm going to do some more tricking. Okay. Yeah. Just mess with you.
Good class, bad class.
And they just have them be
Which
wrong.
class is good?
Ah! Forget everything you thought you knew. Which our family jokes around that's the generic movie tagline for every movie ever. Forget everything. Doctor Strange, forget everything you thought you knew. The Matrix, forget everything you thought you knew. Get Out, forget everything you thought you knew. It's just every movie ever. So awesome. You have created this new class. Mission accomplished. You've added first name and last name to your object, this identity class. It's so successful that you've been hired by major electronic medical records company, and now they're all, you know what? You're so accomplished and so effective that I want you to add BMI to your electronic medical record. That stands for body mass index. Add that to your identity class. Body mass index is a number that's calculated based on your height and your weight, and it indicates, general level of health. Hey, that's just another pair. No problem. We're just going to swap that right in. We're not going to have any trouble at all. And what we'll do is we'll have our constructor so that when someone creates an identity, we'll pass in their height and their weight. They're doubles, of course, because they're numbers. We'll store their name as before, their password. Now we're going to keep a stored BMI as a pair. We'll just create a new pair object with height and weight. And oh no. Wow, 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 wow. Eclipse says we can't do this. Eclipse says we can't do this because when we declared our pair type, what we said was being passed in the constructors were strings. And these aren't strings. No. These are doubles. And Eclipse says, no. I'm responsible for making sure that types are matched. This is a strongly typed language. And so I'm not going to allow that to happen because otherwise you'll distribute code and your off-duty Santa will have a miserable day. Okay, well that means that this code down here is going to fail as well because when we try and get the stored second element from our stored BMI and multiply it times 703, the Eclipse says, well, you can't actually multiply a string times a number. That doesn't make any sense in Java. So this also is bad code. All right, well, back to the drawing board. Actually, it's not that big of a problem because we can just easily fix that. We'll just create a different pair class. So previously we had a pair of strings. Here we're just going to make a pair double, and instead what we're going to store here is we're going to store two doubles. We'll call it stored first and stored second. We'll just recreate the constructor, and we'll reconstruct the getter that returns a double, and the setter will take a double, and the second will return a double. So great, no problem. It wasn't a lot of code. We've just created a pair double, right?
Wrong.
What have we created? Forget everything you thought you knew.
No, that's correct.
Okay.
But it doesn't use these.
It doesn't use those. Those are generics.
That could be a problem.
And this is not a generic class as a result, right?
It's not generic.
It's not generic. It is merely a pair of doubles. It's risky, right? It's so close to lunchtime, and that looks really good. This is not the pair of doubles that we care about, though. When we think about our pair that we made, when we think about storing the first element and the second element, what we're doing with it is completely agnostic to what we're storing in it. It just doesn't even matter for the code that's part of our pair class, what's in there. But what's happening is, because we have to return something with get first and get stored second, the language is actually stopping us from being able to think about this just abstractly or generic. We're really stuck in a situation where we have to define a new class for every application that needs a different type. A pair of strings, a pair of doubles, a pair that's a string and a double, a pair that's an integer and a double, a pair that's a pair of pairs. Anything that we want to do, we have to rewrite that class, which is why generics were developed. What generics allow us to do is talk about parameters generically. That's where the name comes from. Generically, without necessarily knowing what their type is, but without losing the power of static typing. So without losing that power of knowing that what you're storing is what is a particular class. So what we're going to do to create our new pair of generics is to introduce this new syntax. This is the systems programmer. This isn't the applications programmer. This is you as someone that wants to create a class that works with generics. And what we're going to do up there is we're going to introduce the angle brackets in the definition of our class, and we're going to put some identifier up there. And those letters can be anything you want. Traditionally, they start with a capital letter, and traditionally, they're just a single letter. So I put a capital F and a capital S up there to indicate first and second. But what they really are types. And so if you see how they're being used here, you can see that we're creating this pair where our stored first is not of type string or of double, but of type F. And the second element is of type S. And so how is this compiling okay? Well, it's compiling okay because we declared these types here. And so within the body of this class, Java knows enough to say that, well, whatever F is, it's got to be consistent. So when we create our constructor, we're going to pass in something of type F, and we're going to assign stored first to be equal to first. And that's going to be okay because we know first is of type F and stored first is also of type F. So that type will be matched, even though we don't necessarily know what it's going to be at runtime. And likewise, when we come down here and we set the stored element, we're going to say, okay, if we want to change what's in the second element, we can change it to anything that's of type S. And then we'll say this.stored second equals stored second. And so when we're writing this as systems programmers, we don't know what type this is going to be used with. But at runtime, Eclipse can do the work and Java can do the work of making sure that those types are matched so that we get the benefit of compile time checking. So now we change our identity class as such. Now, rather than using pair string, we now are able to use this generic symbology so that when we declare our pair generic, we're going to pass into that class, well, what is F going to be? F is going to be a string. And what is S going to be? S is going to be a string as well. So stored name is going to store a string and a string in its pair. But stored BMI, 2 lines down, is going to use the exact same code, but it's going to be parameterized with different generic types. So that F is going to be a double in this case, and S is going to be a double in this case. And now when we go to use these and we say stored name down here, we'll say, okay, well, our stored name is going to be a new reference to a pair generic where we're storing strings and strings. And so we have to pass in a string and a string. But our stored BMI is going to be a new reference to a pair generic where we're keeping track of a double and a double. And so Eclipse says, well, if that's what you're going to do, then height and width for the constructor, height and weight, better be doubles as well. Same code, parameterized by different type variables. And so now we get all the benefits of type checking, but we only had to write the code one time. And not only does it work here, when we get our stored first, we know that's a string because the way we declared it up here must be a string. But that same stored first down here works as a double because when we declared our stored BMI, we said the first is going to be a double. So this multiplication works okay. Really, really kind of beautiful and elegant, if you ask me. No one did, but I'm telling you. So I just think it's a really, really nice, little bit complicated, but abstraction and encapsulation of what is it exactly that we're doing along the way here. Okay, so basically that's it. I mean, that's 80% of it anyway, as far as generics go. As a systems developer, you can put those type parameters at the top. You can put 1, 2, 3, as many as you want, and then you use them within the body of your code consistently. And then when a application programmer uses your class, they just fill in the types that they want to use with that. So it's about 80% of everything we need to know about generics, and it's basically that easy, but there is a few little details to mention. So that would be the final 20%. All right, so for starters, generics and primitive types don't play well together. So you can't plug in primitive types to generics. And this is one of the reasons why we haven't spent a lot of time talking about primitive types in this class. So in the first example, you can see I'm trying to parameterize my pair generic with lowercase I ints, and that isn't allowed. And that's not allowed because we need some of the properties of objects in order to make our generics work. So that we can't do. The other thing that we can't do is we can't use a generic in an array because, we can't use a generic in an array because an array itself is a primitive type. So we can have, so this is an array of generics. We're not allowed to have that. We can have an array that that's right, an array of generics. So we can't do that because an array is a primitive type, and you can't mix primitive types and generics together. If you wanted to do the code that's on the bottom, what you could do instead is you could make an array list that contains pairs of generics double double, and then you can add as many as you needed to. All right? So do primitives and generics work well together? No. No. You cannot make primitives and generics work together. Just read the slide.
The really big red axes. Little hints.
Little hints. In the pair that we specified, we put no restrictions on what could be filled in that generic, in those brackets there. Sometimes you want to be able to make some restrictions on what classes can be used. And so it's possible when you write your class as a systems programmer, you can put a few restrictions on what kind of classes can be used. So in this case, we made a sort of generic kind of pair. And you can see that we're declaring that our pair is going to take a generic, and it's going to be F and S. And we use F and S throughout our code. Here's F and F, F and S, F and F, F and S everywhere. But by declaring it up here, we say, well, you can't use any type here in F. F has got to be some class that descends from the number type. So things like integers and doubles descend from numbers. And in the second case, S has to be some type that extends from pair double double, which is a little weird, but it has to be something that is either a pair double double or a child of pair double double. Why might you need that? Well, an example why you might need that is because you want to call a particular method on one of your stored elements, and you can't call that method unless you know that method is present in the class. And you maybe only know that that method is present if you say it descends from some particular number. So when you do this, you're kind of breaking the super powerful aspects of generics where you can just use any class, because you're not actually saying you can use any class. You can use some classes. But it exists in this halfway point between writing pair double double where you can only use one class, or writing pair generics where you can use any class. It exists in the hinterland there between the two. Some of the flexibility of both. All right. So here's a question. How, given what we know about pairs, what could we do in order to make a quad, something that keeps track of 4 elements instead of 2? What would that look like? It's coming to me. It's coming to me.
Well, would we make a class that would be?
Let's look at our pair generic. So this is our pair.
We put in commas, and then put in 2 more.
Yep. Okay, so put in 2 more commas. What do you mean by that?
Just 1 more comma.
You mean up here?
Yes.
You do need 2 more commas for 4.
Yes.
Okay, and so what are you going to use for letters? Give me some examples.
T and lowercase f.
Don't use a lowercase because that.
No. T and L.
Totally doesn't matter, right? As long as you're consistent. So then, okay, now you've declared that there's going to be 4 types that you're using here. Where else are you going to need to make alterations?
The next 2 lines, well, you'll add 2 more as stored third and stored fourth.
Great. And then what else are you going to have to do?
And then, what did we say? T third and L fourth.
Here?
Yeah.
Great.
And then stored third and fourth equals third and fourth.
Yep. And you're going to have to just make sure that whatever variable you use there is consistent. Now this allows, if you put 4 different variables up there, that's going to allow you to use 4 different types along the way. Let's see if I can track down where we were there. Let's see. Sorry, I lost myself. Okay, so here's an example of that. This isn't exactly what you said. This is a different way of doing it. So in this example, what I did is I put 4 letters up there, S, T, U, and V. And S, T, U, and V, doesn't matter what they are. They just represent the 4 different types. And instead of making all those instance variables separate, I actually wrapped 2 separate pair generics. So I created pair generics as instance variables instead. This is legit. You can do this also. But my first pair generic is of S and T, and my second is of U of V. I just have to make sure I'm consistent. So you can see in my constructor now, I'm using capital S to be the type and lowercase s to be the variable. And doing the same with T and T, U and U, and V is the type, and lowercase v is the variable. And then I create my pair generic with S and T as my types, and I pass into the constructor lowercase s and T. And then when I want to get the third element, I look at bar, my second pair, and I get the first element of bar, and the fourth is the second element of bar. And this is all abstracted away. So the person that's using this quad generic only knows that the constructor, get first, get second, get third, and get fourth all work. They don't know anything about how I chose to implement it. So I could have implemented this all with my own instance variables. I could have used it with 2 pairs. I could have used 1 instance variable and something called a triple. I could have done anything I wanted here. Because this is hidden from the user, the application programmer, as long as these things have the right behavior, I can do whatever I want along those regards. This enables you to have 4 different types that are stored in your generic. If you wanted to, you could create a quad in which you keep track of 4 elements, but they would all be the same type. And if you wanted to keep track of a quad in which everything was the same type, rather than listing 4 types up here, you would just list 1 type, probably just S. So you kind of scratch out this bit here. And then down here below it, you would make this an S, and you'd make this an S, and you'd make this an S. And then you'd change all the instances of T, U, and V to S as well. And that would still be a quad, but it would be a quad where you only have 1 type for all 4 of those elements. So if you, as someone who's designing that class, wanted that to be the behavior, this is a quad where you keep track of 4 things that are of the same type. You can do that by only having 1 type up there. But we're more flexible in this case, where you can have 4 of the same type or 4 different types. But if you end up having 4 of the same types, you're going to have to list that type 4 times. You see that? See how you as a developer could restrict that to being one type if you wanted to? You wouldn't say SSSS 4 times. You just say S 1 time and then implement that along the bottom. Because that top line up there, this is just about declaring which types you're going to use, not actually using them. So 1 type 4 times versus 4 types 4 times. Okay, another way that you could do your quad is on the right. This is an example of extent. It's kind of cut off up there. But in this case, what we're doing is we're actually extending or descending from another pair generic. So we're using an existing pair. You can see we have extends pair generic up there. And then we're adding to that a second pair called foo. And we're using the parent class's first and second element here in the superclass. And when we want to get the first element, we just inherit stored first and we inherit stored second. But if we want third and fourth, we need to use the instance variable that we're using here. So that's yet another way of implementing it if you wanted to. All right, this is maybe the most confusing bit of the whole lot. Generic types themselves are atomic, meaning that when you declare a type, for example, pair generic string string, that whole thing is one type. And you can't think of it, once you start using it, as being sort of pieces that are actually put together. You compose it, but once it's composed, it's a solid atomic thing. You don't work with it separately anymore. The what? The pair class with the 2 parameterized generic types. That whole thing is one class, and you should think of it in your head as just being its own unique type, as opposed to it remaining a composition of multiple types. You do compose it, but once it's composed, it is its own thing, and it doesn't reference the string type anymore, for example. So let me see if I can show you an example of this. In the first case there, we're going to create something that is of type object, so that's the superclass of all objects. And then we're going to create an integer, which is going to store 10 in it. And then we're going to take the reference of some object and say some object and some integer are now going to reference the same thing. Now that's going to compile okay because object is a superclass of integer. Integer descends from object. And so anytime we need to access some method that's associated with object, it's okay to call that method on the integer class because integers have everything that object has and more. In the second case, we have a method in which we're passing in a number as a parameter. Now a number is a superclass of integer and double. So it's okay to pass in an integer and a double when a number is expected, because inside the body of some method, we're only going to be allowed to use methods associated with the number class. And since integers implement everything number implements and more, and doubles implement everything number that number implements and more, by passing them in, we're sure that they're going to have everything that number implements. But now down at the bottom, we start to run into a slightly different situation. In our pair generic, actually the third one's okay too. In pair generic, when we start with number and we create a pair and we pass into the constructor foo and bar, that's going to be okay because we're passing in things that implement everything that number needs to implement as well. But what we can't do is we can't inherit just part of a class. So on the left side down at the bottom, you can see the green check mark, and it says that double inherits from number, which inherits from object. That's fine. But the second line there, vector double does not inherit from vector number, which does not inherit from vector object. That's what I'm talking about when we talk about things being atomically a type. Although double descends from number, vector double does not. Vector double is its own thing. And so the correct way to think of those 3 classes, rather than thinking of them as being inherited the same way that the parameterized class inherits, the right way to think of them is as they are described here. Vector number and vector double are both descendants of objects, but they're not descendants of each other because they are not double and number and vector independently. They are their own unique class. And so we can see that happening in, let's see, let me see if I can retrace here what's going on. In the top version, we have a method that requires a vector of type number class. And in the bottom, we create a vector that contains doubles. And so when we try and pass in bar to sum, we get an error. And that's because sum requires vectors that contain numbers, and we're passing in vectors that contain doubles. And it's not that doubles and numbers don't descend from each other, it's that vector double does not descend from vector number. And we're passing in a vector, not the individual numbers. And so that the example that you see in the boxes there is assuming this incorrect mental model here, where the correct mental model is here. Give you a second to look at that. Okay? If in some world sum had just contained a parameter which was number, like that, and down here in bar, if bar was just a double here, then that would have been okay. But we're not passing numbers and doubles. We're passing vector numbers and vector doubles, so that's not okay. So again, this is the 20% of generics that gets a little tricky, but not the 80% that you need to know in order to make them work. All right, so how do you go about calling this generic method? What I would like to do is, let's see if we can take a second. Let me see, how are we doing on time? Actually, I think, let me see here. Whoa, sorry. What I want to do, rather than doing this, what I want to do is I want to go back into Eclipse and I want to modify the code that we wrote last lecture before the holiday, where we implemented array list. And what I would like to do is I'd like to modify it so that it implements a generic. Okay? So to do that, what I'm going to do is I'm going to break out of Keynote and I'm going to bring up Eclipse and I'm going to share the project with you for today. And we'll move the code over and I'll show you the process of converting our array list into a generic class. For the programming assignment that you're going to do on generics, what I'm going to ask you to do is implement a pair class, a triple class, and a quad class, a little bit like what we saw in the slides today. And I have some tests that I would like you to run in order to verify that they work all right. Okay? All right, so let's switch over to Eclipse. And connect on Saros. And let's see, I'm connected, okay. So while you guys are doing that, what I'm going to do is I'm going to take our basic data structure implementations from last class, and I'm going to copy them all over. Actually, let's just copy this. Yeah. All right, and should we copy? Let's go ahead and do Q and stack as well, because we're like that. All right, so for today, we're looking at 16, and let's go ahead and share those. Boom, boom, boom. All right, Tim, did you fail?
Sometimes it freezes up on the login screen, so I have to shut it down. So yeah, I just started to.
Okay.
No, I'm disconnected.
Wow. Wow. Tim has a fear of commitment.
Disconnect, wait a few seconds, and then reconnect.
All right. In the meantime, what I'm going to do is I'm going to run all the tests in the code that we just brought over, just to make sure that in my copying nothing broke. All right. So it looks like all of our tests are working great. That makes me happy. It makes me think that our code has some promise of being correct. Get Tim to join us here. Is everything syncing okay? All right, and so which one do we want to start with? Do we want to start with array list or linked list? Audience choice. So much freedom. Linked list. Okay, linked list because Boaz was first.
Yeah.
Okay, so here is our class. Linked list. And now, to be honest, I'm not entirely sure how this is going to work out when we're implementing an interface, but we'll give it a shot. So we know that our linked list is going to, right now our linked list is storing strings, but we want to be able to store anything. And so we're going to add a generic parameter here and see what happens. What letter do we want to use? L. Okay, L is the choice from the audience. All right, so now by adding L, we have now declared that within the body of our object, of our class linked list, we can use the type L. And when someone goes to implement, to use our class as an application programmer, they're going to need to specify what gets stored here. But as of yet, even though we've said that we are going to use L, we're not actually using it anywhere. So the main place that we need to use it is we need to use it in our myNode class. Well, hey, how about we make myNode generic as well? I'm not even sure we can do this, but let's try it. We're just going to give it a different generic variable just to be clear that we're working with different types. And what we know is we know that the data that we're going to store in the myNode class is going to be of type N now, because we're working within the body of just this class. And this class takes N, and it's going to store in N. And we're getting a little error here because the reference that we're referring to has to be referencing something that stores an N as well. All right, so that was a little tricky. I'm using a generic recursive class there. Sort of awesome. All right, so that's fine. That's all well and good here for our myNode class. But when I create this first element, what do I want my first element to point to? Well, it's going to be a myNode that contains an L, because this is what is being passed in up here. So myNode is going to be an L. That L is going to get passed down here. L is going to map to N, and then N will be what we stored. Well, as we come down here to try and implement things now, we say, well, the before reference has got to be a pointer to myNode containing an L, and the after has got to be a reference to the after containing an L. Maybe we should go down and should we just go through in order? Fix it up. All right, so asking if something has a next element, that doesn't require looking at any of the interior data. That's fine. When we want to return the next element, well, we can't return a string because that's not what we're saying that our class contains. We're saying that our linked list holds L items. So we're going to return elements of type L. And now this might be where I complicate the issue with an inheritance. Okay, I wasn't expecting to tackle this, but let's go ahead and change our interface. We're going to make the interface generic as well, and I hope this works. I didn't prep this beforehand. Great. When we add something, we're going to add something of type L. When we get something, it's going to return something of type L. When we remove something, we're going to get the L back. Size, clear, print. Our iterator is going to be an iterator. All right, why? So I just changed the interface for the list. I made the interface for our list now as generic. How come when I did add here, I didn't change the type of where? Why is where still an integer, but what is now an L?
Because where is the reference to the location?
Right. Where isn't about the kind of data that we're storing. Where is about where in the list we're storing it. So that's still going to be an integer. And that's going to be an integer regardless of what we're storing. We can be storing strings or identities or doubles or whatever we want. We still need to be able to get the first one and the second one and the third one, etc. Okay, so we've changed our interface now. Our interface is going to be of type L. So if our linked list is declared on L, then our interface is going to be of L2. And I think that we don't need that anymore. Oh, no. Trapped in obscure Java syntax. Oh, no, that's okay. Unimplemented methods. Okay. So we come down, and next should be returning an L. And why are we complaining? It's incompatible. Let's just keep going. All right, we want to add something. We want to add something of type L. That's fine. I'm getting trapped in generic world. Now the node is going to be of type L. The node's going to contain an L. We're going to add an L. When we remove something, we're going to remove an L. I'm going to go back and clean up the errors beforehand. The thing that we get is going to be an L. It's not going to be a string. We're going to return that. My node is going to be of type containing L. The thing we're going to return is an L, not a string. When we set something, we're going to set something that's going to be of type L. And we're going to, the thing that we changed is going to be an L. We're going to return not a string, but an L type. When we add something like our interface said, we're going to add an L, not a where. And my node is going to contain L's. My node is going to contain L's. My node is going to contain what?
L's.
L's. When we remove something, we're going to get back on. What are we getting back?
L's, right?
Yep.
No, lowercase L. No, bad. Okay.
Good. Not a string, a.
Oh.
Good. We ask for the size. We need to walk down the list, and that's going to require a walker. That's type L. My nodal.
Should we change to Jesus? Because Jesus is always the answer.
Too many characters in this case. I heard a funny joke that you may not think is very funny, but I think is funny. And it was that Jesus' real miracle was having 12 friends when he was in his 30s. I thought that was kind of funny. Okay, so now we've got this iterator, and what's going wrong with our iterator? We need to add the unimplemented methods. Okay, so we need to make sure that our list iterator is also has a generic type. So list iterator, when we get the element back, it's going to be type L. If we want to add something, we have to add types L. If we want to remove something, we're going to get back L's. We'll set something, it'll be L's. All right, and okay. Oh, we're going to inherit our L's from above. Actually, let's do that. Let's change this. I did. This is different than what I'm saying, but now I'm doing it live. I understand what I'm doing now. I like it better. So what I just did is I changed the code so that my node has to hold the exact same type. I'm not allowing my node to hold something different than what linked list holds. So by saying my node and not providing a generic type in the header, but saying it has to hold an element of type L, it's tying whatever we created our linked list to hold into what my node holds. That means I have to go back here and change all these, but it's the right thing to do. Yeah, I would do it automatically if it didn't contain funky characters, which would mess up my automatic stuff. All right, so thanks for your patience as we go through and do the right thing. The right thing eventually. The right thing trademark. Okay. And then our iterator is going to be type L. And what do we have left over? Forgot to return an L there. Okay, so a little bit of complexity with my node class, but we just went through and we changed all of our references to strings that were present in our linked list to now being of type Ls. And in order to do that, we also had to make sure that our interface expected generics, and we had to make sure that our iterator also expected generics as well. That's fine. That broke our array list because when we changed our interface, now our array list doesn't do the right thing. And it also means that our tests that we wrote that are going to be testing our linked lists are also going to be a little bit broken. So let me go through and fix one of them for us. So we're doing our list. Let's take like Boaz's here. You can see Boaz's test that he wrote is now giving us a bunch of warnings because we didn't specifically say what these things are going to contain. We assumed that they contained strings before, but now we're going to be explicit about them and say strings are what they contain. And that's all we had to do to fix the test. So you can see that from the application programmer experience, it's actually pretty clean. From the developer, you have to do your work and do it well, but once you do that, it's okay. So let's go through and fix our other ones. I'm looking at Lisa's test now. Same thing. Just declare that the strings that the types that we're working with in our test are going to contain strings. And now in Tim's case, we do the same thing. Right. And then in Joy's. All right, so if we go back to our JUnit tests and we run it again, hopefully, if we've done our work well, all the linked lists will pass and only the array list elements are going to fail. So it looks like everything that doesn't reference array list worked out fine, and then the linked list are broken. Okay. So where does that put us then? What I will do is I will change the array list so that it takes generics as well. And I will then post that code on Canvas for those following along remotely. And if you guys stay connected for a few minutes, then, well, we'll see how that goes. What we did today is we started introducing the idea of generics. And we did that by motivating it with this example of the vectors and thinking about how we want to make sure that our code is as safe as possible before we distribute it. And one of the ways that we can do that is by helping the compiler know what it is we're going to be storing in our code. That was bad, though, because every time we specified what we were doing with our code, we had to rewrite our whole class in order to accommodate the different types that we wanted. So we had to pair string string and pair double double. And that was just a lot of duplicated code. And so the mechanism in Java that enables us to write the code once and be able to parameterize it with other kinds of types is called generics. That's what the subject was today. And by doing that, by using this special syntax, we only have to write the manipulation of the data one time. And whether it's an array list or a linked list, we can write that code in such a way that it doesn't matter what we're storing. What matters is this higher level organization of the data. And we can write it one time and store whatever we want in it, and we don't lose that strong type checking that we're provided by the compiler. So that's the motivation for it. And so we'll continue working on this on next class. And actually, maybe what I'll do is I'll hold off, and we can do the implementation of the array list maybe together next class. That would be a good way to work through some of the issues with generics and tackle a few other items. I think that's it. Anything online? Nothing? Okay. Any last minute questions or concerns?
you write your own types?
Yeah, that's all class is. Class is just your own type. Okay. Thank you for your attention. I will see you in 22 hours. Ciao.